Go ahead.
Okay, so I'm McDaniel, in case you don't know me. My report was over structural design in extreme wind conditions. This is an example of extreme wind condition, obviously. You can see how big this tornado is against some of the cars and stuff. So this is the structures that we're trying to, that are trying to withstand these kind of wind forces. So some of the wind types that you'll be dealing with are straight line winds. They cause a lot of bending to the exterior walls, large uplift on overhangs. If there was an overhang on this structure here, you get a ton of uplift on that overhang. Cyclonic winds, those are primarily the kind of winds that tornadoes create. They create a large cooling effect on the back end of the building, and then a lot of torque on the building as a whole. You'll notice a large pressure differential in the back end and the front of the building. And then you'll get also downhill winds, which is a big factor with buildings at the bottom of mountains and hills and such. So they're really similar to straight line winds, and here you can see how winds, we've all seen this before, how winds affects our buildings. You're receiving a large push when the wind is on the windward side, and then a pull on the leeward side. So a lot of the leading issues that you'll be dealing with when you're designing for heavier winds are a strong bulk load of wind on the windward side. And then another big issue is flying debris known as missiles. And these missiles penetrate buildings constantly. This is an I-beam that's gone into the ground, God knows how far. A 2x4 or 2x6 that's gone through a concrete curb, a disc that's found its way into what used to be a tree or a telephone pole, and then what seems to be a semi-truck wrapped around what used to be a tree. So you can see how strong these wind forces are and why it's important that we protect the residents inside of homes and commercial buildings. So the pressure differentials is probably the leading cause to the destruction of a building. It causes implosion and ballooning or explosion of the building. There's an example of that here soon. Here's the example of ballooning. So the left is built to code, normal building here in the Midwest, and then the right is fortified with stronger building materials. This failure that you'll notice is at 135 miles per hour, and that's equivalent to an EF2. It's not wanting to show. Come on. That's equivalent to an EF2 or a Category 3 hurricane. So hopefully this will load and you guys can see the video. And basically what you'll notice is that the large panoramic window in front breaks, and that increases the pressure on the inside, which causes a ballooning of the building and similar to an explosion. So again, the window is broken here. The wind then enters the building and causes an explosion, and the wall then fails. As you can see, the stronger building, fortified with better building materials that aren't required by code, isn't even moving. So again, this was built to code here in the Midwest. And you can see the wall then cracks down the side, and the wall completely fails. So you're standing in a CMU building thinking that you're safe, and then you're not. So, tornadoes, these are our specialty. We know about them, especially here in the Midwest. Tornado Alley, of course. You're dealing with EF0 through EF5 rating system. The rating system is based on damage. So a surveyor will come in and determine what kind of, or how extensive the damage is in these areas. And an EF0, you're looking at about 65 to 85 miles per hour. In EF5, you're looking at about 200 miles per hour. So that's the difference between EF0 and EF5. The most common is EF0 and EF1. but EF2 and EF3 account for about 25% of the tornadoes that we have. You're dealing with 111 to 165 miles per hour when you're dealing with those kind of tornadoes. And again, our rating is only to 90 miles per hour, so you can see what our code kind of does in those winds. Another wind testing video. Again, the home on the left is built to code. Hopefully this one will play. Good. Home on the left is built to code. Home on the right is a fortified construction. Similar to what you'll find in a hurricane region. They've got hurricane foundation ties, stronger timber ties. This is only at 92 miles per hour. This is 2 miles per hour over what our code is rated for. Completely destroyed. Similar to what you see in Moore, except Moore was an EF4, where those winds were about 160 miles per hour, I believe. So the biggest difference between these homes is the door over here opens inside the home, the door over here opens outside the home. So you're getting a breach in the exterior. You'll see this door fly open here, and then the house will begin to fail. You're getting a breach inside the home, and the wind is entering and creating a large pressure differential, which then makes the home explode, practically. Again, built to code, not built to code, over standards. And obviously is holding strong. So once this door opens here, you'll see this door frame completely blow out. So that's kind of you would assume that the windows would break first, and that they may not be using actual glass windows for the cleanup, but the door just completely flies off the hinges out of the frame, and the roof failure there. That's why they have you stay in the first floor of your home. And then the back end, the beauty shot of the whole thing flying out. So, just to bring it to reality, your family is staying in this home hoping or thinking that it's safe for tornadoes in this region, when clearly it isn't. This is rated just an EF1. Moore was an EF4. Joplin was an EF5. It's really hard to design for EF5 tornadoes because they're so strong, but we could design for all the way up to probably EF2 or EF3, to be honest. So some of the design considerations when you're designing homes in these regions, or businesses in these regions, maybe changing the shape of the building. We've constantly stuck to a rectangular design because of the space inside. You save space per square foot of ground coverage when you design with 90-degree angles and such. If you switch to circle or more of a half spherical building, you're going to be experiencing less wind forces on your building, less failure. Monolithic domes are basically domes that are built sheet by sheet, really similar to what Doran was going over with his analysis. And then also changing out screws and tying your foundation, or tying your structure to the foundation. So some of the design considerations, again, normal construction, you're going to be dealing with screws that are just normal screws that you see every day. And then here are the high-strength screws. So that's some of the differences that you can see in higher strength. Here's some of the wood ties that we use today. You think they're enough? And then here's some of the wood ties that they use in hurricane-prone regions. But these are better options, especially this one. They'll tie the roof down to the main structure. And then the consequences, you're always going to get high property damage. Death rates are going to continue. Here are some of the more recent events that have caused some really high death rates here in American history. These are 3rd and 7th in the nation. And then insurance rates continue to go up. You're dealing with in Moore or Southwest Oklahoma City, insurance rates went from about $1,000 a year to $3,000 a year in the course of about 5 to 10 years. So you could see lower house rates. That's why building stronger and building more expensive in the front end will be helpful for you. So So architects can inform their clients, structural engineers can be responsible for recommending these changes, and then contractors and supervisors should be responsible for making sure that these changes are adequate, or the quality of construction stays high. And then Bonnie suggested maybe we live underground, since she wasn't sure I went ahead and do that. Any questions?
Don't hobbits live underground?
Yeah. Yes?
Didn't you say the house that has the door that goes in was inspected, the other one had it going out?
Mm-hmm.
Yeah, exactly. So the wind was able to break the door frame and blow the door in, which increased the pressure inside the building. So that ended up making
So
the building
because the
basically
hinges
explode.
let it swing open and
Mhm.
force it? Okay.
Right.
Cool.